If a 10-gram mass is oscillating from a spring at a frequency of 2.5 hertz, what's the magnitude of the spring constant? So I'd like to use the formula omega is equal to square root of k over m to do this question. I prefer this formula. It's simple compared to the other two alternatives that are there, but you can use any of those that were on the key concept slide if you like, if you have them written down. For this one, the information I'm given, though, needs to be worked with a little bit because we're told that the spring, or it's oscillating from spring at a frequency of 2.5 hertz. So that's really F is equal to 2.5 hertz. So omega has a relationship to F of 2 pi F, which means I can calculate what the angular frequency omega is by saying 2 pi multiplied by 2.5 hertz. And when I run that into my calculator says about 15.7. I might, let's see, we're working at 3 significant digits, and I always like to say let's keep at least a couple more for round-off's sake. And so maybe it's actually 15.70796327. So maybe if I just go 2 more for 08, that usually makes you safe. And that would be in inverse seconds since it's an angular frequency. And then the thing that we're being asked for here is the spring constant, right? The question we're looking at is k is equal to what? So if I look at this original formula here, and if I square both sides, I would get omega squared is equal to k over m. Now if I multiply both sides of that by mass, I get k is equal to mass times omega squared. And then I could use the mass given of 10 grams. I'd like to convert that to 0.01 kilograms so that I'm working in base units because that will probably be easier for me to interpret in terms of what units I think the spring constant should have. And then we'll multiply. I'm just going to write here the 15.708. So if you do that on your own in your calculator, if you'd like, that probably will give you a correct answer. You have to square it though. If you don't square it, you won't get a correct answer. But that'll probably give you a correct answer within rounding to this question. I have still in my calculator the original unrounded number for this, and I'm going to put that into this expression, and that gives me 2.4674011, which at this juncture I'm going to round that to 2.47 based on the desired 3 significant digits of accuracy. And this is kilograms per second squared, but I'd like to restate that as newtons per meter because that's the customary units used for a spring constant. So let's go ahead and check that answer, and it looks like it matches.